Calorimetry video number 2. So what we're going to do in this video is actually talk about how we can actually measure Q, or the energy change that's involved in a physical or chemical process. So in order for us to actually measure this, to do this in a lab, we have to make use of something called a calorimeter, where calorie, think of that as heat, or energy, meter meaning to measure. So a little etymology there. What calorimeter means: measure heat, measure energy. And we have different types of calorimeters, but the one that we use most often, at least in a high school setting, is a coffee cup calorimeter, where in a coffee cup calorimeter we have an outside styrofoam cup. I know, so high tech there, styrofoam cup. And then we have another styrofoam cup that gets nestled inside of it. We fill it with water and we stick a thermometer down in there in order for us to measure that change in temperature. So we might carry out a reaction and measure how the temperature of the water changes in order to make some assumptions about the energy change of that reaction. Or we might put an object into that water and measure how that temperature changes. But again, it's this calorimeter that's going to let us actually determine Q. It's going to let us actually measure that change in energy. And those of you moving on to AP Chem, you'll see, or you'll learn eventually, that there are other types of calorimeters. We have a bomb calorimeter, which we can also use to measure the energy change of a process. And there's other methods as well, but the calorimeter is the cheapest and easiest way for us to measure the energy change of a process. So as I kind of mentioned already, a calorimeter can be used to measure the energy changes of a physical or chemical change. And kind of the one big assumption that we make, which can give us quite a few errors with our calculations, is we assume that all of the energy that's lost or gained by the system, so in other words, all of the energy that is given off or absorbed by what we put, is going to equal the energy that's gained or lost by the water. So again, common thing that we do in calorimetry, maybe we want to figure out the specific heat of an object. Remember from our prior video that the specific heat of an object is a way for us to identify it, because each substance has its own. So we might take a piece of copper metal, heat it up, throw it in the water, measure, or shouldn't have said copper metal there. We may take a piece of metal that we don't know, heat it up, throw it in the water, and measure the resulting temperature change as a way to calculate that specific heat. So the assumption we make is all of the energy given off by that piece of metal is going to go just to the water. And again, we know that's not true. The styrofoam might get some of that energy. The surroundings, the air, the thermometer are going to gain some of that energy. So there are some issues with the assumption, but again, kind of the assumption we make is what's called Q equals negative Q, that the energy lost by the substance is going to equal the energy gained by the water. And what I want to focus on is how we solve these problems. Again, we're going to stay very simple with calorimeters. In years past, we've used a calorimeter to actually calculate the energy of a chip, or the energy change in a reaction, which the energy change of a reaction we call delta H. It's enthalpy. But really, for our purposes, we're just going to use it kind of with Q. And let's try some problems together. All right. So we have a 2.80 kilogram sample of metal with a specific heat of 0.43 joules per gram times degree Celsius. We heat it up to 100 degrees Celsius and then place it in a 50-gram sample of water at 30 degrees. What is the final temperature of the water and the metal? So again, another key assumption of calorimetry, besides energy lost equals energy gained, and I shouldn't even say assumption, but a big principle, is that the final temperature of our two objects will be the same. That we're going to have that exchange of energy until we reached what's called thermal equilibrium. So in other words, we have our two substances that are going to exchange energy until they reach that same final temperature. And really the one big assumption, remember, we make is Q equals negative Q. So our energy that is gained equals our energy that is lost. And again, we'll see this a bit more with an online lab tomorrow. It's really, among the many reasons, many unfortunate reasons we're doing distance learning. Not being able to do calorimetry labs definitely hamstrings us a bit. So when I say Q equals negative Q, for a lot of us, the positive Q, the water in the calorimeter, is going to be absorbing energy, and the metal that we heat up to a higher temperature will be losing energy. Because again, the water, its temperature is going to go up. It starts at a lower temperature. It's going to absorb the energy that is released by the hotter piece of metal. So in these sort of problems in a calorimeter, again, we call them Q equals negative Q because we have that exchange of energy. And these problems involve kind of setting Q equal to negative Q and plugging in. So we have our side of the water. So on one side of this, we have MC delta T for the water is going to equal negative MC delta T for the metal. So let's plug in what we know. So again, positive side is going to represent the water. So our mass of the water, 50 grams. Our specific heat of the water, 4.184 joules per gram times degrees Celsius. And change in temperature for the water. Okay, well, the problem's asking us the final temperature. So that's what we're trying to figure out. The final temperature minus the initial. And I can't just put in delta T because each substance has a different initial temperature. And then each substance is also going to have a different change in temperature. So if we're solving for final temperature, I always have to put final temperature in as our x minus the initial temperature. And then our metal, we got to be careful here. I might be tempted to put 2.8 kilograms, but notice it's joules per grams in our specific heat. So I got to change that to grams. I'm going to leave units off here so I can fit this in. And our final minus that initial. So this is our setup for that Q equals negative Q type of problem. All right. So at this point, it's a lot of math. And the first thing that I would do is just multiply my mass and specific heat on both sides. So 50 times 4.184, I get 209.2 times our final temperature minus initial temperature of the water is going to equal, let's go negative 2800 times 0.43 for the metal, negative 1204 for the metal, times the final temperature minus that initial temperature of 100 degrees for our metal. So after I multiply mass times specific heat, now I'm going to go ahead and distribute on both sides. So I get 209.2 times that final temperature, and 209.2 times 30, that'll be minus 6276. It's going to equal negative 1204 times the final temperature. And then don't forget, guys, distribute that negative sign. It's negative 1204 times negative 100. So it should be plus 120400. Again, I did mass times specific heat. And then in my next step, I distributed. Now I want to go ahead and group like terms. So I'm going to add 672, 6276 to both sides. And add my 1204 TF to both sides. I know it's so annoying, right? So 1204 plus 209.2. I get 1413. 0.2 times my final temperature is going to equal 120400 plus 6276, 126676, and then divide both sides by 1413.2. And I get my final temperature, I think 3 sig figs, as being 89.6, and let's see, that would be degrees Celsius. So once some time had passed, after we put that heated up piece of metal into the water, the final temperature of both the water and metal would reach that equilibrium temperature of 89.6 degrees. Kind of a handful. Don't worry, I'll do another one. Again, kind of the key assumption we make when we put that heated up piece of metal into our water, they have that same final temperature, because again, we're going to have energy lost equaling energy gained. And again, this is just one way to use a calorimeter. Fortunately, we're just kind of using, well, we're not really getting all of them here. Are we ready to try another one maybe? Okay, let's try, number 5. So the specific heat of mercury is 0.033 calories per gram times degrees Celsius. If 152 grams of mercury at 75.0 degrees Celsius is placed in 145 grams of water at 23.5 degrees Celsius, what will the final temperature be? So again, we have mercury, we have water. So we know that this is another Q equals negative Q problem. So we're going to have to plug into both sides. And again, water is starting at the lower temperature, so we know that's going to be positive Q. It's going to absorb energy. We call that endothermic. It's positive. Our mercury starts at the higher initial temperature, so we know the mercury is going to lose energy. That's going to be the negative side of this. And that would be exothermic. All right, so let's plug in the water. So the mass of water, 145 grams. Our specific heat of water, 4.184 joules per gram times degrees Celsius. And our change in temperature, well, we don't know final, but minus the initial of water, 23.5 degrees Celsius. And then that's going to equal our mass of mercury times its specific heat times its change in temperature, and ignore my terrible units there, of final temperature minus 75. So it looks good, right? I know my scribbles are kind of on the screen there, but do you see any issues? Well, I do. I see different units. I see joules on one side and calories on the other. Do you think we can use that? If you're screaming no at the screen, you're correct. We can't use that. Our units have to match. They have to be the same. So we got to change one of these specific heats to have the correct heat energy unit. For me, I think the easiest to change is water. We know 4.184 joules is the same as 1 calorie. So I'm just going to plug in 1 calorie there instead of 4.184 joules. Now let's do our math. So let's go ahead and multiply both sides. So we get 145 times 1. Guess what? 145 times that final temperature minus the initial for water. It's going to equal 152 times 0.033, which is 5.016. Should be negative. Forgot my negative there. Times our final temperature minus the initial temperature of 75 for the mercury. Now let's distribute. So I get 145 TF minus 145 times 23.5, 3407.5 is going to equal negative 5.016 TF. And again, don't forget that negative sign will distribute. Negative 5.016 times negative 75. I get positive 376.2. Now let's group like terms. So let's add that 3407.2 to both sides, and add our TF to both sides. Oh, happy birthday, McConan. Good for you. Your old high school friend. He's a good guy. Okay, we get on our left side 150.016 times that final temperature times X is going to equal 3407.2 plus 376.2. Sorry, that's 307.5. We get 3783.7. And then divide both sides by that 150.016. And we get that final temperature, I think 3 sig figs, as 25.2 degrees Celsius. Wow, handful there. So again, the key to these calorimetry problems, Q equals negative Q, plug in for the water on the positive Q, the metal on the negative Q, and just keep track of those negative and positive signs. Good luck finishing this. Again, if you have questions, you can always reach out and email your teacher.